Let's look at a solution for the mult table problem. So write a function called mult table that takes a single number, and return a list of lists that represent a multiplication table of that size. An example of size 3 multiplication table would look something like this. I had somebody ask about this, if it needed to be visually returned in a grid like this. This is the reason it's presented in a grid like this is for our benefit. Python has no ability to distinguish between this and this. So unless we did some special formatting thing, this list is equivalent to this list. So yeah, that's just why that's there. Okay. So let's write this function, def, and this takes in a single number and return a list. Okay, so this is going to be the size. I'm just going to call it in though. And then from here, we can have our, we want to return a list. I'm going to call the list a table, because it's a list of lists and it's sort of a, grid or a matrix or a table. So a table makes sense to me. Return table. Get that out of the way. So I'll say for I in range n, and then for j in range n also. So I want to be able to multiply every number by every other number, right? So I want to start with 1 and multiply it by 1, then 2 and multiply it by 2, 3 and multiply it by 3, etc., right? So I have to be able to adjust this to start at 1 and go to n plus 1. And now let's just test this. We'll print I times j, and we have some things here for us to expect. Let's comment these tests out so we can get some more sane output. So I should expect 1, 2, 3, 2, 4, 6, 3, 6, 9, and I get 1, 2, 3, 2, 4, 6, 3, 6, 9. Okay, cool. So this proves that I can produce those numbers. Now I have to place them into the appropriate lists. So I've got my table up here, and this is, for many of you, hopefully starting to look like a pretty straightforward accumulator pattern. But here's the trick. It's an accumulator pattern within an accumulator pattern. So I'm going to call this, we're going to have another accumulator called row. I'm going to call it row because it's essentially going to be the nested lists, and I'm going to think about those as the rows. So row will equal an empty list, and for every j in range 1 to n plus 1, we're going to row dot append I times j. And after that's done, let's just print row every time just to check on it, see what it is. And I should get these three lists, a list of 1, 2, 3, then a list of 2, 4, 6, and 3, 6, 9, 1, 2, 3, 2, 4, 6, 3, 6, 9. So this, well, this does look quite a lot like that intended output. But notice I'm just printing 3 independent lists. That's not, the function isn't yet returning the appropriate value. But since I checked it there, I can just, at this point, at this indentation level on line 15, row has been fully assembled, right? In other words, this for loop has completed its cycle. It's completed all of its iteration, the inner for loop, and row is fully completed. So now that it's fully completed, I can table dot append row. And now let's just run this. And you can see we append every row into table, and table now has the correct value. Cool. So something to look out for is this, where row is here. I've helped a couple people with this problem, and I've noticed several people wanting to start it up here and sort of thinking like, well, how can I manage that? You know, if I start it up here, my code will execute, but we're not going to get the right value. So all the lists have all the same values. The nice thing about starting it here is that it resets its value to empty every single time, right? So for every time we go through a loop of this outer loop, the first thing we do is we reset row. And the first time this runs, actually we initialize row, and then from there on out, we're just resetting its value, clearing it out to be a new list that we can append I times j to, and then append that new list to table. So that's something to think about when solving this problem. Cool. Hope that was helpful.